Good evening, everyone. I am Abhay Singh Rajput, and we are going to present the presentation on topic design and fabrication of coreless organic substrate. My teammates are Varad K Pawar, Hitesh Mehar, and Timothy. So these are the outlines of our presentation. We are going through these topics during our presentations. So this is the introduction about the coreless organic substrate. So coreless organic substrate are the type of the PCBs packaging that omits the traditional rigid core materials such as fiberglass reinforced epoxy. This coreless design results a thinner and lighter substrate which are particularly advantageous for the modern electronic devices required for the compact and efficient packaging solutions. So in pictures, the general architecture of the coreless organic substrate is shown, and in second picture, the advantageous flexibility of the organic core substrate is shown. The coreless organic substrate are an advanced packaging technology designed to enhance the electrical performance and achieving ultra-thin profiles. The substrates are utilized in various applications, including high-performance computing, which provides the GPU benefits to reduce signal delays and improve power distributions. Also, they are used in mobile devices such as smartphones and tablets, which provides thinner profiles of these items. So this is a comparison between conventional and coreless organic substrate. So conventional organic substrate has organic core that provides mechanical stability. But in place of this, in coreless organic substrate, there is no core present, reducing the thickness and improve the electrical performance of the chip. And the basis of the wire and interconnect structures in conventional plated through holes for interconnections, which require drilling through the core. But in coreless, uses stacked copper layer and coppered field vias, enabling the final routing and higher density. In conventional one, featuring non-reinforced resin surrounding to the PTHs and limiting design flexibility. But in coreless, these are the thin dielectric layers with a core improving the signal integrity of the microchips. And also in compare BGA, the BGA pads are on the bottom layer in conventional one, and in coreless the BGA pads with pocket which may enhance the thermal and mechanical performance of these chips.
Okay, now talking about design consideration for coreless organic substrates, the points that we need to keep in mind are warpage control. So for controlling warpage, for reducing warpage, the design which is used is glass reinforced prepack, which also results in improvement of mechanical stability and optimization of copper distribution to balance stress across the layer, and also implementation of symmetric stack ups to minimize internal stress. And secondly, the via and interconnection design, the options that can be implemented for via formations are using stacked vias instead of staggered ones for higher density routing, and optimization of via size to maintain electrical performance while ensuring manufacturability. And third point is electrical performance optimization. For electrical performance optimization, we can use ultra thin copper foils, which ranges from 1 to 3 micrometer, which helps in minimizing the parasitic effect. Parasitic effect as inductance and impedance effect, and optimizing the trace width and spacing to maintain signal integrity. And fourth one is manufacturing process adaptability. We can use different manufacturing processes such as modified additive plating to make sure there is fine line patterning, and implementation of carrier based processing for better handling during manufacturing, and some more processes like alternative dielectric material can be used, like Ajinomoto build up film for basic application needs. And fifth point is embedded component integration. Embedding component in coreless substrates require precise layer stacking and reliable interconnects. And for that, we can use KGS, also known as known good substrate, which can reduce yield loss and ensuring diaped metallization, which supports laser drilling and chemical cleaning. And lastly, thermal management. We know that heat dissipation is needed for high performance application. So utilization of copper filled vias can be efficient for heat conduction, and optimization of dielectric thickness, which will balance the thermal performance and mechanical strength.
Important aspect of the design is fabrication of a package to form a substrate. And this can be done by forming vias, then depositing the seed layers, and then filling the vias to form interconnection and form the RDLs. The choice of via formation methods depends on substrate materials, via size, and required interconnection density. The via formation can be done by mechanical drilling or the lasers, as laser will give the smaller vias with high precision to ensure fine features, but mechanical drilling will give the cost-effective solution to form a via for the size in between 30 to 100 micrometers. These via will serve as electrical connections between the different layers in a multi-layer substrate. The electroless the electroless copper plating is used to create a thin conductive layer inside the via and the surface of the substrate. These processes rely on chemical reaction to deposit the copper. These seed layers provides the conductive base for the subsequent electroplating, which ensures the uniform copper coverage inside the via and surface traces. Which also improves the adhesion between electroplated copper. RDLs are used to reroute the electrical connection in advanced packaging, which can be formed through the photoresist electroplating by photolithography, which enables the fine pitch interconnection for advanced semiconductor packaging, also improves the signal integrity and reduces signal losses. The proper insulation between the layer is important to control the leakage and avoid any short circuit. It can be done by introducing the dielectric lamination and build-up layer formation. The dielectric lamination are the thin dielectric layers such as Ajinomoto build-up film or polyamide, which can be used over the patterned conductor. The planarization ensures the smooth surface through controlling the lamination, and if needed, electromechanical polishing can be used to ensure to reduce the surface roughness. Then by drilling or the laser ablation, vias can be created in the dielectrics to expose the underlying copper pad and the connect by connecting the two different layers. By repeating this process of a patterning, plating, dielectric lamination to build RDLs to form a subsequent metal layers, which ensures the tight alignment between the layers to form the high density routing.
Now, let us look at the advantages of Coreless substrate. It, the most significant advantage is that it reduces thickness and weight. This is due to the fact that Coreless substrate eliminates the core area, reducing overall thickness and weight, making them ideal for compact, lightweight devices like mobile electronics and wearable devices. It also improves electrical performances due to the absence of braided through holes, which lowers parasitic resistance, inductance, and significantly enhancing integrity for high speed and high frequency applications. Uh, Coreless substrate also enhances thermal management due to thin and uniform layers in Coreless substrate, which improves heat dissipation and reducing the risks of overheating in high performance applications like 3D packaging or stacked ICs. It also leads to cost reduction. This is due to the fact that eliminating the core layer reduces material costs and simplifies some manufacturing steps, potentially lowering packaging cost by about 15 to 20% in cost productions. There are a few challenges in porous substrate fabrication, and the most significant challenges are warpage, and this is due to the fact that without a central core, the build-up layer are thinner and more prone to bending. Coefficient of thermal expansion mismatches between copper dielectric layer and adhesive induces residual stress during curing, and this causes misalignment in chip placement during flip chip assembly and can negatively affect electrical performances. There is also challenges like mechanical stability due to the absence of reinforcing core, which makes the substrate more flexible but also more prone to chipping and cracking during handling and assembly. There is also challenges like reliability issues due to long-term durability, and this is due to increased warpage and mechanical fragility that leads to solder joint failure, delamination, and reduced overall package life. Another challenge in porous substrate fabrication is also about thin profile handling. Due to ultra-thin nature of porous substrate, it makes them very fragile and difficult to handle during manufacturing and testing, and assembling them without bending or breaking them is quite difficult. And these are the references that we use to make and correct data to make this PPT. Thank you, and that's the end of our presentation.